Good morning and good afternoon, everybody. This is Dennis Smith. We are going to talk about pumping systems today and try and get a good understanding as to what happens in those pumping systems with surge, slam, water hammer, and look at how Desert can assist you with valve selection and energy savings to eliminate or minimize those types of problems. So to start with, let's see if we can gain an understanding of the surge pressure causes and effects. Surges are caused by abruptly changing the fluid velocity. And the faster you stop and start the flow, the higher the surge pressure. And what we want to try and do is avoid that surge pressure, which causes damage to the system. Now, in a pumping station, the velocity changes are caused by normal starting and stopping of the pumps, and it's also caused by an electric power failure when the pump is running at maximum flow. This animation here shows a pump with a check valve pumping into a line and into a tank. And what this is going to simulate is how the surge wave travels back and forth in the pipeline. The first thing that happens is that when we lose power to the pump, we have a negative pressure surge that travels down the pipeline. It's a low pressure surge. It reflects off the reservoir and comes back and encounters the closed check valve. And now it in turn creates a high pressure spike. That travels back down to the reservoir, comes back and reflects off the check valve again. So these pressure spikes, both positive and negative, if we did not have friction in the pipeline, they would continue forever. But with the friction, each pressure of that surge wave is less than the previous. So now if we look at how fast the surge wave travels, we can calculate that, as you see by this equation designated by the small letter A in the top right-hand corner of the screen. And that factors in the bulk modulus of our fluid, which is normally water, the pipe diameter, the pipe modulus of elasticity, the pipe wall thickness, pressure class. But in general, what we see with the surge wave speed is the more rigid the pipe, the faster the surge wave travels. When we look at ductile iron, cast iron, steel pipe, it's traveling 3,000 to 4,000 feet per second. Your softer pipes, such as HDPE and PVC, those pipes are soft, they expand under pressure, and the surge waves go a little bit slower. So without doing any calculations, we can obtain wave speed if we Google on the internet the type of pipe we're using, the diameter and pressure class. Most pipe manufacturers will publish their water hammer wave speeds, and you see a table here for PVC pipe. So we don't even have to do a calculation to determine wave speed. So why do we need the wave speed? The wave speed allows us to estimate the surge pressure in the pipeline. And the way that we do that is that we use what we call Joukowski's equation to do a quick calculation or estimate of the surge pressure. And we can do this without using any high-level transient analysis software. The surge wave magnitude and pressure, either positive or negative, is designated by delta H. That's calculated by the wave speed times the change in velocity divided by gravity. So obviously gravity is a constant. We know that. That's 32 foot per second squared. We get the wave speed from the pipe table. So the only thing we're missing is the change in velocity. That's very easy to calculate as well. Let's say that we're flowing in a 12-inch line at 2,500 gallons per minute, and that's 10 foot per second velocity. We lose power to the pump. We've gone from 10 foot per second or 2,500 gallons per minute to 0. So our delta V would be 10. So we can easily calculate or estimate the surge pressure magnitude, which is designated by delta H. Now, that said, when we calculate that delta H, it needs to be added to the system static head to get the total head in the system for that surge event. So just be mindful that when you calculate delta H, it must be added to the static head to get total system head for the surge event. The next thing that we look at when we do our surge calculations is something called the surge critical period, which is designated by T sub C. And T sub C, or surge critical period, is one round trip of the surge wave. And as we saw earlier in that animation, we had the negative pressure wave travel down to the tank. It reflected off the tank and came back to the pump station. That's the critical period. That's one round trip for the surge wave. And we calculate that by using this equation you see here on the screen. It's 2 times the pipeline length divided by the wave speed. So we know now how long it takes for that high pressure surge, that damaging surge, to come back to the pump station. Now, if we again look at the pressure versus time graph, as I said earlier, without friction, that surge wave is going to travel back and forth indefinitely in the pipeline as an upsurge and a downsurge, or positive surge and a negative pressure surge. But what happens is, with friction in the pipeline, the friction absorbs that energy. And one of the things that we look at is, for every additional critical period we stop the flow over, we reduce the pressure by 50%. So let's say, for example, we've calculated our delta H surge pressure to be 1,000 PSI. We've also calculated our critical period to be 5 seconds. So if we stop the flow in 5 seconds or less, we're going to surge the system to maximum intensity, which would be 1,000 PSI. If I stop the flow in an additional critical period, and we now do that in 10 seconds, I cut the pressure in half. I reduce it to 500. If I add another critical period and go to 15 seconds in decreasing or increasing the fluid velocity, I cut the pressure in half again, from 1,000 to 500 to 250. So generally, stopping the flow over 10 or more critical periods will result in acceptable surge magnitudes and will not damage the pump station. This is important because this relates to timing. As I said, surges are caused by abruptly changing the fluid velocity. So in a pump station where you're using a variable frequency drive pump, calculating 10 critical periods gives you an indication, when you're doing your pump selection, of how slowly that pump needs to ramp up and ramp down if you're using a variable frequency drive pump. If you've got a constant speed pump and that pump turns on and off instantaneously, generally you're using a slow opening and slow closing pump control valve. And that pump control valve, then we can determine how we set the opening and closing speed of that power actuated pump control valve by calculating a time that's equal to 10 or more critical periods. So we've defined surge. That's abruptly changing the fluid velocity, and it's a pressure change. Let's now look at slam. Slam is a little bit different, and I'm sure most of you have experienced slam in a pump station. Slam is the noise produced when the disc of the mechanical check valve is in the open position as the fluid column reverses. When that fluid column reverses, it encounters the backside of the disc and forces that disc to the closed position, creating a check valve slam or bang. So the next thing I'm going to show you is a little animation video. It's of a check valve in a test lab. It's a wafer type swing check. You see the wafer body here, the shaft, the disc, and this wafer body check valve is installed in a plexiglass piece of pipe so that we can see what's going on inside. And what you're going to view here in this video are a couple things. First of all, we're going to shut off the pump. You're going to hear the breaker trip. There's going to be a noise associated with that. And then we have that liquid that flows away from the pump station as a downsurge. One critical period later, that flow reverses and comes back to the check valve. The check valve is in the open position, and you'll hear the check valve slam. And then what you'll see is after the check valve closes, you'll see the surge wave that we discussed, which is the upsurge and the downsurge. And each of those pressure waves will become less in intensity due to the friction in the pipeline, eventually bringing that fluid column to rest. That's the turning off of the pump. Here's the check valve slam. Now you see the surge wave theory. Upsurge, downsurge. Upsurge, downsurge. And if you would time that, that's one critical period between the upsurge and the downsurge. And you see by the fluid in the pipeline, each surge pressure is becoming less intense because the friction in the pipeline is absorbing that energy and bringing that fluid column to rest. So that's slam and surge. So the $1 million question is, how do we prevent that? Which valve is best? As I said earlier, abruptly changing the fluid velocity creates surge. So we ask ourselves the question, does normal pump startup and normal pump shutdown produce unacceptable surge pressures? If the answer is no, you can utilize a mechanical check valve. Generally, you'll see mechanical check valves used in conjunction with variable frequency drive pumps. So under normal operation, the VFD is ramping up and ramping down over 10 or more critical periods, and we don't have those surge pressures, so we can use a mechanical check valve. So the next step in the decision process is, with our mechanical check valves, what type of check valve do we select? There are so many different types out there on the marketplace. This slide shows your AWWA swing check, a rubber flapper check, slanting disc check. We have a center guided disc check valve here. And depending upon the engineer's requirements in designing the system with input from the end user, we consider the fluid media, the pressure type, total cost of ownership, initial cost, operating cost, maintenance cost, and things of that nature to select the right valve for the application. And at times, it's a very difficult process, especially for an engineer who doesn't do a lot of pump station design. For example, the AWWA swing check valve is available in 6 different configurations with just that one type of valve. It can be a plain shafted valve, as you see here. It can be provided with an outside lever and spring, maybe an outside lever and weight. It could be provided with a side mount air cushion, a bottom mounted oil cushion, buffer, or dash pot, or a side mounted cushion, buffer, or dash pot. So again, how do you know which valve to select once you've determined that you wanted to use the AWWA swing check? What type of closure device? That's where the engineers and representatives at the Zurich can assist you in proper valve selection. And as we go through the presentation here, we're going to give you a better understanding of some of that thought process. So let's ask ourselves the question again. Does normal pump startup and shutdown produce unacceptable surges? If the answer now is yes, we should be selecting a slow opening, slow closing pump control valve. Those are generally used in association with constant speed pumps. With a constant speed pump, it's either on or off. It's either zero flow or max flow in a very, very quick period of time. So there's no gradual acceleration or deceleration with a constant speed pump. In fact, when you turn off a constant speed pump, it generally produces the same surge pressure or same surge magnitude as a loss of power because there's no gradual coast on like you see with a VFD. So to gradually reduce the fluid velocity, we use a pump control valve. Now, what is a pump control valve? Pump control valves are power actuated. They're generally controlled by either a hydraulic cylinder, as you see here, or maybe an electric motor actuator. There's many different styles, types, and configurations. But essentially, these are slow open and slow closing to control that fluid velocity under normal pump startup and normal pump shutdown. And then, of course, they're configured to fail close on loss of power to the pump to protect the pump from backspinning. The most commonly used configuration in the industry is a cylinder-operated pump control valve, as you see here. And that cylinder-operated pump control valve can be powered with air, water, or high-pressure hydraulic fluid. Depending upon the application, you might use plant air. If it's a clean water pump station, you can use the water in the pump station to control the cylinder itself. If it's a wastewater pump station and you've got a city water line somewhere in that building for a wash basin or a restroom, you can use that city water to control the cylinder attached to a wastewater valve. And the configuration is generally a 120 volt single phase ASCO Red Hat type solenoid that is energized or de-energized that switches the flow path to the hydraulic cylinder. And the hydraulic cylinder will be configured with needle valve speed controls. There'll be one for opening speed and one for closing speed. So again, how do we determine that opening speed and closing speed? Well, you run through your calculation, you take your critical period once you determine your wave speed, and then we multiply that critical period times 10. The example we used earlier, our critical period was 5. So we would set these opening and closing speed controls for 50 seconds or almost 1 minute of operation for that pump control valve to open and close. And what we do with the pump control valve is we start the pump against the closed valve, we energize the solenoid, and now the solenoid begins pressurizing the cylinder, and we open that pump control valve slowly against a running pump at the rate set on the opening speed control. Same process for pump shutdown. We don't turn off the pump. We de-energize the solenoid, and we now put pressure to the cylinder through a closing speed control set at 10 critical periods or 50 seconds. And we close that pump control valve against a running pump. Once the pump control valve reaches a near closed position, maybe 95 to 98% closed, those valves are generally configured with, and if I can go back a slide here, they're configured with a limit switch, as you see here on top of the valve. That limit switch interfaces with the pump and turns off the pump. So we close the valve against a running pump. Once the valve is nearly shut, we trip the limit switch that interfaces with the pump and turns it off. So if you're using high pressure hydraulic, when we talk about total solutions, if you don't have an air system available, if you don't have potable water to power a cylinder, some customers use high pressure hydraulics. High pressure hydraulics are available from a multitude of manufacturers in addition to Zurich. They can be standalone systems, as you see here on the right, or it can be a central hydraulic HPU system that may control 5 pump control valves in your pump station where you've got 5 pumps. The other thing that we've got to be aware of is how do we control all this? When we're using a pump control valve, we've got to stop and start the pump and open and close that power actuated control valve, whether it's controlled via solenoids or an electric motor operator. Generally, you can have a systems integrator do that for you, but there are also valve manufacturers such as Zurich who manufacture a pump control panel, and that pump control panel can do the interface for you for single system, single source responsibility. So now let's move to the cost of pumping. This equation here you can find on the internet. It's published in your machinery handbooks. Its pumping cost in dollars per hour is a constant times your flow rate times the head loss of the valve you're using, the specific gravity of the fluid you're pumping, your cost per kilowatt hour. How much do you pay for electricity? Is it 5 cents a kilowatt hour, 8 cents? And we divide that by a constant times the pump and motor efficiency. So this is calculating how much electricity is needed to push the fluid through your pump control valve, whether it's a lever and weight swing check valve or a motor actuated ball valve or cone valve. And we can do a comparison to see which valve makes the most sense for a pumping application. Generally, when you have applications where you have continuous pumping, such as a finished water pump station in your water treatment plant, or maybe a sewage lift station that runs 18 hours a day, lifting that wastewater to the treatment plant. The more efficient the valve, the more efficient the system. That's when we start to consider valves like the AWWA C507 metal seated ball valve. It's a 100% port circular waterway, so that when that valve rotates to the open position, it's like looking down an open piece of pipe. So it's very, very efficient. But with these efficient valves, there's a lot higher initial cost associated with that efficiency. So this type of C507 ball valve would be a great selection for a finished water pump station that runs 24/7. But you wouldn't want to use this in a storm water pump station that runs once every 50 years for your 50-year rain event for 10 or 12 hours. It just doesn't make sense to spend the money if you're not having a sufficient amount of runtime. Now, when we come to surge and slam, we've showed you that surges are caused by abruptly changing the fluid velocity. Worst case scenario is a pump running and a total loss of power to the system. With a check valve, whether it's a slanting disc or a silent check or a lever and weight, lever and spring, air cushion, or a ball valve or cone valve, we can get those valves to close quickly on loss of power to protect the pump from backspin. And they can close quickly, and they can also close quietly without slam. But just because they close quietly does not mean that you're not going to have problems in your pump station. Here's a gauge on a discharge header. We've just lost power to our pump. Our check valve was a lever and weight with an air cushion. It closed quietly. We think everything's okay in the pump station, right? Well, we still have our surge pressure, upsurge and downsurge. And if that high pressure portion of the spike is more than what your pipe is designed to withstand, the next issue you're going to have is something like this. You could rupture the pipe. You could have a catastrophic failure. So how do we protect the system from that catastrophic failure? We use surge relief valves. So the title of the presentation, surge prevention and protection. We want to try and prevent the surge if we possibly can. But on a loss of power, you can't. So we have to protect the system. We use a surge relief valve, which is a pop safety valve. We install that on the discharge header, and it opens when the high pressure surge comes back and limits that surge pressure to an acceptable level. As we look at a pressure versus time graph of the surge relief valve operation, The red line is with no surge protection. So we have our down surge and our up surge one critical period later, and that surge wave continues. If this red surge wave spike here is more than what the pipe can withstand, you're going to have a catastrophic event. So the surge relief valve is generally set, and its characteristic curve is the green line. It opens at about 10% higher than the pumping pressure. It limits the pressure rise to an acceptable level so that we do not damage the system. So in the first 25 or 30 minutes here, we've thrown a lot of information at you. Calculating surge wave velocity, critical period, surge pressures, surge slam, water hammer, what type of valve to select. There's so many different styles and types out there. And if you're not doing pump station design on a regular basis, it becomes overwhelming. So there are companies out there like the Zurich that have products to assist you. The product that we have at the Zurich is called a BSI, or Basic Surge Investigation and Valve Selection or Suggestion Report. This BSI, we have a data input form. This data input form is available from our local representatives or our website. And essentially you enter the data, the pipe, length, material, wall thickness, pumping head, static head, flow rate. Is it a VFD pump? Is it a constant speed pump? And we take that information and we run that at no cost to you through our proprietary software. And this is just a snippet of the results where we calculate the velocity, the surge wave speed, which is A, we calculate the critical period, the surge magnitude, and we also can size the surge relief valve for you. In addition to that, we can recommend the right valve for the application. We can recommend the total system. We can start with air valves on the discharge of the pump. We can recommend the appropriate type of check valve, mechanical check or pump control valve. If it's a mechanical check, we can recommend whether you should use a lever and weight or a lever and spring or an oil cushion or an air cushion. If it's pump control, we can recommend maybe motor actuated or hydraulic cylinder actuated using air or water pressure. We can also recommend the appropriate isolation valves on the line, whether they be butterfly valves for clean water service or plug valves for wastewater. We can also size and recommend the surge relief valve for surge protection. And we can also recommend, if need be, the controls if you're using a pump control system. So with the Zurich's team of local reps and factory engineers, we're ready and able to assist you with all of your pumping system applications.